Today's topic takes us back to Science 10. And Science 10, if you remember last year, we learned a law called the first law of thermodynamics. The first law of thermodynamics says that energy can't be created and it can't be destroyed. You can transform it from one type to another. In other words, kinetic energy can become potential and potential can become kinetic. But you can't destroy potential and you can't destroy kinetic and you can't create it either. We're going to rename that law now because the name that we used in Science 10 doesn't translate as well to what we do in Physics 20. It's the same law with a different name. It's now going to be called for us in Physics 20 the law of conservation of energy. Energy cannot be created, it cannot be destroyed. It can be transformed from one type to another. Now, sometimes it looks like energy is created. Sometimes it looks like energy is destroyed. My car sitting in the parking lot has no energy right now, right? I start it up and drive away, now it has energy. I just created energy. But I didn't really create energy. I transformed chemical potential energy into kinetic. Now, I don't have a way in Physics 20 of calculating that chemical potential energy. That doesn't mean it's not there. We're transforming one type to another, not creating. Similarly, when I'm driving down the highway at 100 kilometers per hour and a deer runs out in front of me and I slam on the brakes, I come to a stop. It looks like energy is destroyed. I had kinetic energy and now I got nothing, right? Well, it wasn't destroyed, rather it was converted into thermal energy. If you were to feel the tires right after you come to a quick stop like that, those tires would be hot because of thermal energy generated, not created, but thermal energy generated as a result of the conversion of the kinetic energy in the car to the thermal energy. In fact, if you look behind the car, you would probably see skid marks on the pavement from the tires. One of the reasons you see skid marks is some of the rubber wears off on the pavement. But one of the reasons why you see skid marks on pavement, more so than you see skid marks on concrete, is because when you slam on the brakes quickly, it generates enough heat that it actually melts some of the tar in the pavement, and that kind of rises to the surface. So some of the skid mark is not actually rubber, but rather it's tar from the road, that's coming up because of the heat that's generated when you stop your car quickly. So again, energy isn't destroyed there, it just looks like it is. It's really just transformed from kinetic energy of the car, the motion of the car, to the thermal energy in the wheel and in the road. Does that make sense? Energy always stays the same. Like it never is created and it's never destroyed, even when sometimes it looks like it is. Now, when are we going to use this new law of conservation of energy to solve a problem? Well, we're going to do one today, and then we're going to do the second one in about a month. So we're going to focus on this first one today. I'll put a little star by it because that is the one that's applicable for us for the test next Wednesday. When we have a change in height, when an object experiences a change in height, we're allowed to do the law of conservation of energy. Now, that doesn't mean that everything that we've done so far when an object has fallen or risen is out the door now. We're still allowed to do what we did. Like, it's still all valid. But now we have another tool in the toolbox. When we have a change in height, we drop an object. We throw an object up into the air. Okay, an object rises, an object falls, or maybe it's dropping straight down. Maybe it's going up into the air like this. Maybe it's a roller coaster that's going down a hill like this. Or maybe it's a roller coaster that's going up a hill like this. When the height of an object changes, we can use this law of conservation of energy to analyze the problem. Now, the other situation which we're going to focus on in about a month is when you have a spring or an elastic. A spring or an elastic that causes something to speed up or slow down, or that causes a change in speed. We won't worry too much about that right now, but we're going to end up in about a month analyzing problems involving a spring or elastic causing a change in speed, which is going to go very much like what we're going to do today. It's going to look a little bit different because the equation for potential energy will be different. Okay, so when do we do it? For now, we're going to do it when we have a change in height. How do we do it? how do we do it? Remember, change in height, conservation of energy. Don't get confused here. We did work, okay, when an object gains energy, just because you see energy doesn't mean it's conservation of energy. When an object gains energy, that's work. When an object loses energy, that's work. When you have a change in energy, that's work. Okay, there's still all these situations that we learned with work that still apply. Now we're just saying specifically when there's a change in height, we can do this law of conservation of energy. So how do we do it? How do we do it? Well, I want you to draw a diagram. Not a free body diagram, but just a diagram that shows what's going on. And then 2, set EI equal to EF. What am I really doing there? EI is equal to EF? I'm saying that if energy isn't created and energy isn't destroyed, the energy that I start with is going to be equal to the energy that I end with. Next, I'm going to sub in mgh and 1/2 mv squared where appropriate. In other words, you're going to ask yourself, do we have kinetic energy at the beginning of this problem? Do we have potential energy at the beginning of this problem? Do we have kinetic at the end? Do we have potential at the end of this problem? And every time you answer yes, you're going to sub in one of these equations. And then you're going to sub in your numbers and solve. Here's your example, number 15. It says a 1,000-kilogram roller coaster begins at a speed of 5 meters per second at a height of 50 meters above the ground. It rolls down the track to ground level. How fast is the roller coaster moving when it's halfway down? So here's my diagram. This is step 1, right? My diagram, step 1. Here's my car up here. It's moving at a speed of 5 meters per second, and it's at a height of 50 meters. We want to find the speed when it's halfway down. So there's step 1. Now step 2 is to say EI is equal to EF. And why do we say EI is equal to EF? Well, because the energy at the top here, right up here at the top, it's got to be equal to the energy right here, halfway down. If we don't create or destroy energy, then the energy at the initial point is equal to the energy at the final point of this question. Now, step 3. Step 3 is to sub in equations 1/2 mv squared and mgh into this EI is equal to EF. Let's say at the beginning of this problem, at the initial point of this problem, do we have potential energy? Yes? How come, Kelvin? Yes. Yeah, because there's a height. If you have a height, you have potential energy. Is there kinetic energy at the beginning of this problem? Dylan, is there kinetic energy at the beginning of this problem? How come? Since moving at 5 meters per second right here at the beginning, right? So you want to change your answer? Is there kinetic energy at the beginning of the problem? Yes, because it's moving, right? Sometimes you have one, sometimes you have the other, sometimes you have both. But in this case, we have both. Now, halfway down, Andrew, do we have potential energy halfway down? Yes, we do, because there's still a height, right? We're going to say it's mgh final. Do we have kinetic energy halfway down? Iana, do we have kinetic energy halfway down? Yeah, because it's moving down. Yeah, it's still moving. So it's going to be 1/2 mvf squared. Now, let's, oh, look at this. This works out nicely. Mass appears in every term, which means you can cancel if something appears in every term. Now, you don't have to do that because you have the mass. You can sub it in there, but it's a little bit easier to sub it into our calculators if we don't need the mass. 9.81 times 50 plus 1/2 of 5, the initial speed squared. 9.81 times the final height would be 25 meters plus 1/2 of VF squared. Okay, 9.81 times 50 is 490.5. This is 12.5. 25 times 9.81 is 245.25. Combine these terms on the left side, we get 500 and 3. And then we take the 245 over by subtracting, right? What does that give us? 503 minus 245.25 gives us a value of 257.75 on the left-hand side. How are you going to take that half over? Multiply by 2 or divide by a half. Gives you 515. Then you're going to square root it. When you square root it, you get an answer of 22.7 meters per second. So this roller coaster at the bottom of this hill is going at 22.7 or 23 meters per second. So you're going from 0 to almost 100 kilometers per hour in a time of just under 3 seconds as you free fall almost 50 meters down this roller coaster.
You just love being able to scare people.
Does that make sense? Now, we don't really have time to finish up question B, but we can at least set it up. In question B, we're going to say EI is equal to EF. The initial energy will once again be potential and kinetic because it starts at the same place. But what will the final energy be if it makes it all the way to the ground? Do we have potential energy when it reaches the ground? No, we're on the ground. Do we have kinetic energy? It's moving when it reaches the ground, right? So it just becomes 1F mvf squared. This becomes easier, right? Because we have one less term to put in there. We don't have this term in the second question. Now, what's happening in terms of conversions here? When this roller coaster goes down the hill, we're losing potential energy. It's not destroyed, rather it's being converted to, yeah, there is some sound and heat, but mostly it's going to be converted to kinetic energy, right? Let's assume that there's no loss of energy due to sound and heat. Luke, you're absolutely right. There will be sound and heat generated, which means the initial energy won't quite be equal to the final because we lose a little bit. But if we assume it's 100% conversion there to kinetic energy, then no sound, no heat, then we would find that it was a conversion of potential to kinetic. Does it make sense?